The some major properties when we are dealing with the stability of a CFD, stability in CFD. So the properties of numerical methods or the major properties which are crucial for the stability algorithm are consistency, stability, convergence, conservation, and boundedness. So first is consistency. Basically, the discretization of a PDE should become exact as the mesh size tends to zero. So when I am talking about the um, discretization of PDE should become exact as the mesh size tends to zero. This means that the truncation error should vanishes. So this is the consistency. So the basically the consistency we the vanishes the truncation error. So the discretization of PDE should become exact as the mesh size tends to zero. Second is the stability. So the stability numerical errors which are generated during the solution of discretized solution should not be magnified. This is the stability. So in stability, the errors that are generated must not be magnified. The third one is the convergence. So the numerical solution should approach to the exact solution of PD and converge to it as the mesh size tends to zero. So when we are uh, discretizing the our solution, so the solution must approaches to an exact solution, and it must be converges to its mesh size tends to zero. Now the fourth one is the con- conservation. Conservation underlying conservation laws should be respected at the discrete level. So, for example, artificial sources things are to be avoided. Boundedness means the quantities like densities, temperature, concentrations should remain non-negative and free of spurious wiggles. These properties must be verified for each component of the numerical scheme. So for stability, or these are the following, these are the major criteria which are crucial to the performance of numerical algorithms. So first is consistency, second is stability, third is convergence, fourth one is conservation, and fifth one is the boundedness. So these are the five major criteria. Now basically this is the relationship between discretized equation and differential equation. Truncation error should vanish as the mesh size and time step tends to zero. If, for example, pure convention equation del u by del t plus v del u by del x equals to zero. So in the case in space, you it is the depends on times. So n plus one, and this is for x. So it's I plus one, and the central difference so must be order two. Taylor expansion series. This is the Taylor expansion series uh, for spatial, and this is for the for x. Now this equation plus this minus the value of del u by del t del u by del t plus v del u by del t del x with respect to n and I is negative. This is generally the equation. So plus this is the constant added, and this constant must be equals to this value. So when I am talking about the difference between or the discretized equation and differential equation relationship. So this is the basic relationship. So the residual of the difference scheme for the exact nodal value. So UGM must be U delta X and M delta D. So now moving forward, von Neumann stability analysis. The problem of the stability is per- pervasive in the numerical solution of the partial differential equation. Von Neumann analysis is the most commonly used, and it was invented by John von Neumann. It begins with the writing a finite Fourier series, expansion of the numerical solution, and then looking at the decay or the amplification of each mode in the expansion. So the most common notation of the stability for PD is without a doubt von Neumann stability. Assume we have a Fourier expansion in space. This is the Fourier expansion given. So the sum is the our f or the Fourier frequencies now taken for u just one Fourier term u del xt equals to ut exponent of I and fx and evaluate it at xj and tn to get ujn utn exponent ifj del x. So to simplify notation, we can write un equals to utn. Then these are the general uj minus 1, uj plus 1, un plus 1. These are the general stability.